Imagine that there's a blue ball like a basketball falling onto the ground, bounce and stays on the ground. Let's zoom in onto the picture. What we will observe is just purely a circle with a straight horizontal line that touches the ball. Notice that the way the two objects touch with each other is kind of ideal, in which there's only one point in touch or intersect, or say the two objects only share one point. And this point is what we called the point of intersection. And the line below is called a tangent or a tangent line, which is defined having only one point intersected with the sections of curve. There are no two or three or more points of intersection, and along the curve of the ball, it can have multiple or infinite numbers of points that made out of a circle, which means that every point can correspond to their own tangent line that can fully lace around the circle. And for the curves that are not closures like a circle, every point, as long as it's on a smooth curve, can have its own corresponding tangent line flowing through the curves. And the question is, how we represent the tangent of a point? It's very simple. Let's zoom onto the picture. Just say we randomly pick one point on the curve and want to know about tangent. But notice that I'm going to call this red line the ideal tangent line, since it's drawn by the computer, and it is surely very precise. The way we reach this precise drawing is by drawing an imprecise tangent line. Specifically, we still randomly pick one point at either the right or the left of the point we have already drawn. Say right, we pick another point at the right side, at some distance from the left point. The next thing is making a straight line that passes through these 2 points. But let's first move the right point a little to the left. And what we can observe is that the angle between the two lines is varying as the right point changes position. And it's obvious that the angle is narrowing down as the right point moves towards the left, and down to a very small one. And the two lines become very similar, though a small narrow gap at the top. But we can try to best eliminate this gap by continuing to move the right point towards the left point. But the right point never really reached the left point, with a nearly infinitesimal interval between them. Thus, we can have a basic conclusion that we have 2 points A and B. When point B approaches A, the orange line tends to become the red tangent line. This is very clear and you get this intuition from the animation, but mathematicians would always like to see for a more simple and elegant expression for this. So instead of saying A and B, we want to find out their x-coordinate value, x and x0. So it is equivalent to say when x0 goes to x, the two lines tend to overlap. But we can also say the interval delta x between x and x0 goes to 0. According to what we have learned in the middle school, the tangent is geometrically defined as delta y divided by delta x. So the orange tangent k0 will be delta y over delta x. But we might feel this improper to say when something goes to something, something happens. So mathematicians designed a new symbol called limit, which also seems to express a precondition like saying when something happens. But in this case, we're not using a right arrow anymore. Instead, we use an equal sign. Generally we speak, the limit of delta y over delta x as x0 approaches x is k, and you will learn in more detail in other courses, but just treat it as a signal for a condition like when in this case. Next, we can try to expand this expression to a more detailed one. We might try to rewrite the delta y or making substitution by first denoting the y-coordinate values of A, which is fx, and for B, it is surely fx0. And it is also true to say fx plus the interval delta x. So delta y will be the y-coordinate difference between the 2 points, which is the fx plus delta x minus fx. So this will be our final expression. Just make a simple summary for this method. If we want to know the tangent for one point on the curve, just define another new point on the curve, make a straight line that passes through them, and narrow the distance between the 2 points. Then we derive an approximation for this tangent line. This method is applied to every point on the curve, and it's applied to every smooth curves. However, we do not always use the letter k to represent the tangent value, since it is very easy to mess up which function we want to represent when we have multiple expressions. So, to be more targeted on which function is, we would just use the function itself and add a prime on it, called f prime of x. Another way to express it will be dy over dx. The d also means delta, which represents the interval like triangle delta, but the only difference is that it doesn't have the symbol limit delta x goes to 0. We will explain the difference between d delta and triangle delta in the next video. See you!